So here's another situation where we're looking for an antiderivative, and you're faced with an antiderivative. You don't have a formula that works because this antiderivative is a product. It doesn't seem like U substitution is going to work, at least not initially, because of these powers on these trig functions. Doesn't seem like integration by parts is a good choice. Although the integral is a product, I don't think your derivative or integral is going to get a lot simpler if you start taking derivatives or integrals of either of these two pieces. So here, what you need to make use of is you need to make use of the fact that you do have powers of sine and cosine multiplied together here. And the nice thing about this particular integral is that what we can do right away is we can rewrite sine to the fifth as sine of x times sine to the fourth. If we do that, what we can then turn around and do is we can say, let's let u equal cosine of x. If we let u equal cosine of x, then the derivative of u with respect to x is going to be negative sine of x, and then du over negative sine of x is what dx is going to equal. So if I try to do this substitution, I'm going to leave this sign there. I'm going to have u replacing cosine, and that's going to have to be squared. And then in place of this dx, I'm going to put du over negative sine of x. What happens with this sine of x that I kind of peeled off of these other four is it cancels with what I have down here when I go through the substitution steps. I do pick up this factor of negative 1, and the other issue is I'm going to have a sine to the fourth power sitting right here. And that's a bit of an issue. You want all of your variables to be u's. You don't want a mixture of u's and x's when you're going through a substitution like this one. And so what you can say about sine of x to the fourth is that can be rewritten as sine of x squared squared. Why is it beneficial to rewrite sine to the fourth with a sine of x squared? Well, if we think about a trig identity, the Pythagorean identity, it says this. I can replace this sine squared with 1 minus this cosine squared. So if I apply the Pythagorean identity here, I'm going to have 1 minus cosine squared, right? Sine squared of x is going to equal this 1 minus the cosine squared. Well, rather than putting 1 minus cosine squared, I'm letting u equal cosine. Why don't I just toss a u squared here? So I've replaced sine squared with 1 minus cosine squared, replaced the cosine with a u according to the substitution that we were talking about a few minutes back. I do still have to square that quantity, but if you look at this integral, and I can't forget about this negative, I'm just going to pull it out in front of the integral. And if you look at this integral, this is one that you can actually manage with. Now you do still have a little bit more algebra to take care of before you're going to be able to successfully develop your antiderivative, but the algebra here should be pretty simple. It's just a matter of foiling this, right? I can't distribute that exponent, but if I wrote this as 1 minus u squared, so a little more scratch work over here, 1 minus u squared times 1 minus u squared, right? That's how I can re-represent this quantity. And if I actually do the math, first times first gives me 1, outer times outer is negative 1u squared, inner times inner is negative 1u squared. Those will combine to negative 2u squared. And then last times last gives me a u to the fourth. Still have this u squared sitting there. I do still have a product here, and that's an issue within an integral, but now you can go ahead and you can distribute into that quantity, and you no longer have a product. So when I distribute u squared into the 1, I'm looking at u squared into this next piece, minus 2u to the fourth, and into the last piece I'm going to add those exponents, and I'm going to get u to the sixth. This is now an integral that we can do pretty easily. It's just power rule for integration. And if we go ahead and do that integral, we're going to end up with adding 1 to each exponent and dividing by each new exponent. So that'll give us minus 2u to the fifth over 5 on the second piece, and then plus u to the seventh over 7 on the last piece. This is an antiderivative, so I'm going to have to tack on my plus c. And then the last thing to do here before you box it up and move on, you want to get the original variable back in place of these u's. The original variable was x. We know u is equal to cosine of x. So our bottom line here, our final answer here, should end up looking something like this. I'm going to distribute in as well on this line, so I'm going to have negative cosine cubed of x, right? I'm putting cosine back in place of this u. I'm distributing the negative into that, so that'll make this a plus 2 cosine to the 5th of x over 5. And then minus, right, distribute the negative into that as well. Cosine to the 7th of x over 7. Leave your plus c there, and there you have it. Anytime you're dealing with a product of powers of sine and cosine, and one of the powers is odd, like we were dealing with here, what you're going to want to do is you're going to want to kind of peel off one of those factors from the quantity that's raised to the odd power, like I did initially, right? I took one of these sine of x's, wrote it here, kind of let it hang out to serve as something that would successfully cancel in a substitution step. Used the Pythagorean identity to get rid of the rest of those signs. Had a little bit of algebra to do, but not too bad of an antiderivative once it was all said and done.